I already reserved my air ticket last week, so now it's confirmed. So I'm not going to be here after Thanksgiving break. Okay, so this is one of the important chapters. Okay, so we are going to do a lot of math problems in this chapter. So in the next exam, most of the weight goes to this chapter. Okay, so almost 75% of your test grade comes from this chapter. Okay, so in this chapter, we're going to talk about chemical reactions and reaction stoichiometry. Okay, so chapter 2, we talk about chemical compounds. So now we are going to understand the reaction between two different compounds. That's where we need chemical reactions. And also when we talk about chemical reactions, there's a way to quantify chemicals in a chemical reaction. And that's why we need this reaction stoichiometry. Okay. So first we are going to talk about chemical reactions and how to balance the chemical reaction and the types of chemical reactions. And once we have that covered, we will move on to the chemical reaction stoichiometry, which is going to be the calculation part of this chapter. Okay. So first, let's understand what are chemical reactions. So chemical reactions are going to be reaction between two different chemicals. Sometimes it can be one reactor and one product. So there are different types of chemical reactions. But if it's a chemical reaction, there's a way to write that on a piece of paper. So we're going to use that chemical reaction on a piece of paper. So area of study that examines the quantity of substances consumed and produced during the chemical reaction. Okay, so that's called stoichiometry. So based on the law of conservation of mass. So I don't know how many of you remember this. So we covered this from chapter 2. So that's one of the theories in the Dalton's atomic theory. So law of conservation of mass means at the end of a chemical reaction and at the beginning of a chemical reaction, mass is same. Mass does not change. So that experiment was done by Antonio Lavoisier in 18th century. So he had a simple experiment and he measured the mass at the beginning and end of the reaction, and it was a conserved property. Okay, so we are going to follow the same thing during a chemical reaction. And first, how do we know there's a chemical reaction? So there are some physical evidence to understand or identify chemical reactions. So mainly there are 4 or 5 physical evidence, and those evidence are formation of bubbles. So when we mix two chemicals, we're going to see bubbles coming out of that reaction mixture. It's an indication of a chemical reaction. And also change in color. So it can be in the liquid or it can be on a metal, something like that. So like pink color solution turns into purple. Then it's indication of a chemical reaction because that new chemical has new properties. So color is a new property. The next one, production of a solid. So when you mix two liquids, let's say one of the new product is insoluble in the solvent, then it will precipitate. So those are the insoluble solids. So that's another indication of a chemical reaction. And also some reactions get released to the environment and some reactions can absorb heat. The change of heat or change of temperature is another indication of a chemical reaction. Okay. So in addition to that, acid bases are chemical reactions. So now, once we have a reaction, there should be a way to write it on a piece of paper. So we are going to use the formula or molecular formula or ionic formula for the reactant and products to write on the paper. Okay, so when we write a chemical reaction on a piece of paper, it should follow the rule conservation of mass. So which means we have to have the same mass on the reactant side and the product side. Okay, so how do we do that? It's based on the number of atoms. So if we have the same number of atoms from the elements we have, so if we have the same number of atoms and same type of atom, okay, then it is balanced because we are not going to add a new atom or we are not going to destroy any of the existing atoms. So we are going to follow that by counting number of atoms in these molecules. So if we look at this reaction, this is a simple reaction which produces water from hydrogen gas and oxygen gas. All these compounds are covalent compounds. So you have the formula. So if we look at these formulas, water is a molecule which has one oxygen and 2 hydrogens. So now this reaction written with 2 water molecules. So which means number of hydrogen atoms in 2 water molecules is going to be 2 times 2, 4. So you can see there are 4 hydrogens on the product side. So then we have to have the same number of hydrogen on the reactant side. So hydrogen comes from hydrogen diatomic molecule. So it's a molecule which has two hydrogens in one. So in order to get four hydrogen atoms, we need two of those. Now you can see there are four hydrogen atoms on the reactant side. So if you look at number of oxygen on the product side, so each water molecule has one oxygen. So total oxygen is two. So total number of oxygen is two on the product side. So we need one oxygen molecule to get two oxygen on the reactant side. So simply we are counting number of atoms. Okay, so every chemical reaction is balanced based on types of the elements and number of atoms. Okay, not molecules, not any other thing. So it's just number of atoms. Okay. So when we write a chemical reaction, if it is more than one reactant or more than one product, we're going to use plus symbol in between reactants and products. And also there are two sides of the reaction. So those two sides are reactants and products. So arrow is pointing toward the products and the other side of the reaction is going to be reactant. Okay. So we can have different number of reactants and products. In addition to that, normally in a chemical reaction, we indicate the physical state of each of these reactants and products. So under experimental condition, whether it's a solid, liquid, or gas, so we are going to indicate the physical state of a chemical, physical states of chemicals in the reaction. Okay. Do I have a slide for that? Oh, it's right here. So I'm going to give you only four. Those four physical states are within parentheses, simple, let's stand for solid. Okay, so within parentheses, immediately after the chemical formula like this, carbon dioxide and experimental condition. So this D is the physical state, which is gas. S solid, G gas, L liquid, and AQ aqueous. AQ means aqueous dissolved in water. So that particular chemical dissolved in water. Okay. That's the meaning of aqueous. So water is a solvent. Stand for aqueous. So now we can see those four physical states is solid, L liquid, G gas, aqueous. As an example, if I write sodium chloride like this. So this is pure sodium chloride, which you buy from the Walmart. But if I write it like this, sodium chloride, aqueous. So now this is a sodium chloride solution, salt solution. Okay, so that's the difference between S and Aq. So Aq means this is a solution. Salt solution. Solution has solvent and that solvent is water. So when the solvent is water, it says Aq. Okay. So those are the main things that you are going to see on a chemical reaction. Okay. So now I'm going to give you an imbalanced chemical reaction and then we're going to balance those chemical reactions by counting number of atoms. Okay. So let's start from a simple reaction. So there are different types of reactions and this type of reaction is going to be combustion and I will cover this later. Combustion reaction. The combustion reactions, one of the reactants is going to be oxygen gas. Okay. And if it's a combustion reaction, all the combustion reactions are going to produce carbon dioxide and water. So normally we're going to use fuel to do our combustion reaction. So that fuel is going to be hydrocarbon. So hydrocarbons are the molecules with carbon and hydrogen. So as an example, natural gas. So natural gas is a hydrocarbon and its molecular formula is CH4. Here it's a gas. So in this reaction, all the reactants and products are gases. So now we can see this is a chemical reaction. So methane gas, oxygen from air, produce carbon dioxide, water, plus heat. Heat is not a chemical. Okay, so that's why it is not in the reaction. Heat is just an energy source. So we can use this heat to cook our food. So we don't need that in the reaction because heat is not a chemical. So now it's a chemical reaction and we can't change any of these formulas. So we talk about chemical compounds from last chapter. So these subscripts are fixed. So these are covalent compounds. Yes, all are covalent compounds. So then those subscripts are fixed. So we can't change that. Okay. So now let's count number of atoms. If it's a chemical reaction, it should be same on both sides. First, I'm going to count number of atoms for reactants. So we have two reactants. So before we count, we should be able to identify types of elements. So there are three types of elements: carbon, hydrogen, oxygen. So before we count number of atoms, we should identify the number of elements. So there's one carbon, four hydrogen, and two oxygen. So now count is the subscript number. So by default, symbol indicates there's one atom of that element in the molecule. So there's one carbon because there's no any number greater than one. So there's one carbon in this molecule. So methane is a simple molecule like this. It's an organic molecule. There are four hydrogens bonded to one carbon. Okay, like that. So one carbon and four hydrogen. So that four is the subscript. And oxygen is a diatomic molecule. So there are two oxygens like this. So that's why it's O2. There are two oxygen atoms. Oxygen atoms in the reactant side. Okay, so we counted all the atoms for reactant. So now we are going to do the same thing for the product side. So we have two products. Okay, so if it's a chemical reaction, Dalton's atomic theory, point number 3, during a chemical reaction, atoms are either created or not destroyed. So we should have all three types of elements on that side. Okay, so we no new atoms, we are not going to lose any of the existing atoms. So you can see carbon in carbon dioxide. Next one is hydrogen, hydrogen in water, oxygen in both. So you can see same type of elements on that side. Okay, so now we are going to count the number of carbons on our product side. So how many carbon atoms on the product side? One. So carbon present only in carbon dioxide. That's one carbon. How many hydrogens on product side? Two. So this subscript number is the number of hydrogen. 2. How many oxygen atoms are on the product side? 3. Okay, so that's important. So there are 2 oxygen atoms in one carbon dioxide. So 2 oxygen from carbon dioxide plus there's 1 oxygen in water. So 1 oxygen. So 2 plus 1 total is 3. There are 3 oxygen atoms. So sometimes same element can be present on multiple reactants and products. Any question after this? So now you can see we don't have the same count. So we have same number of carbon. So carbons are balanced, but no hydrogen and oxygen. So we are missing 2 hydrogens and we are missing 1 oxygen on reactant side. Okay. So then it is not going to be balanced. So now we are going to balance this reaction. When you balance the chemical reaction, you can't change any of these subscripts. So you can't touch those subscripts. The only thing that you can change is the number in front of a molecule. Okay. So you can put any number in front of a molecule. So you can get 1 water molecule, or you can get 2 water molecules, or you can get like several oxygen molecules. So these numbers are called stoichiometric coefficient. These numbers are called stoichiometric coefficient. So it basically tells you how many molecules are going to be in the balanced reaction. Okay. So now we can see this is not a balanced reaction, and we are going to change these numbers and balance this reaction. Okay, so first carbon is already balanced, so we don't need to touch carbon, so which means we don't need to change number in front of carbon dioxide. The next one is hydrogen. So we have 2 less hydrogen on product side. So hydrogen present on in water. So if we can get another water molecule, it will increase the number of hydrogen by 2 and oxygen by 1. So if we add another water molecule to this side, so 2 from this, that makes 4. Okay, so instead of writing like this, simply we are going to write a number in front of the molecule. So this tells us there are 2 water molecules now on product side. So when you put a number in front of the molecule, it will change the count on your elements. So you should update these numbers. So when you put a number, it will always change your existing count. So now we are going to count the new number of hydrogen and oxygen because this number affects only on hydrogen and oxygen. So new number of hydrogen is going to be number in front of a molecule times the subscript. Okay, so always the number in front of the molecule times subscript is the count. So it's 2 times 2, new number of hydrogen is 4. And also it will change number of oxygen. So now we have 2 water molecules, 2 times 1. So there are 2 oxygen from water. Okay, there are 2 water molecules, each has 1. So 2 times 1 is 2. And 1 carbon dioxide. So 2 plus 2. New number of oxygen is 4. So now we have balanced carbon, hydrogen, and last one is oxygen. So if you look at oxygen, the molecule we have on the reactant side. So we need 2 more oxygen atoms for the product side, reactant side. So simply we can add another oxygen molecule. 2 times 2, new number of oxygen is 4. So now all 3 are balanced. Any question? So this is how we are going to balance any chemical reaction. So simply we count the number of atoms, and if it is not same on both sides of the reaction, we can change the numbers in front of a molecule. So if we did not change any of these numbers, by default those are ones. So normally if it is 1, we don't write it. Okay, so by default that formula tells us just at least 1 molecule from that compound. Okay. So in this reaction, stoichiometric coefficients are 1, 2, 1, and 2. Okay. So which means in order to completely burn 1 methane molecule, okay, so this is methane, we need 2 oxygen molecules. And then it will produce 1 carbon dioxide and 2 water molecules. So if you're not going to follow that ratio, we will not be able to use the, one will be excess, like let's say we have 2 of these, and if we use 2 of these, 1 to 2, 2 to 4. So we don't have enough oxygen. The oxygen runs out first. So it will be limited on oxygen, and the other one will be excess. So when we make a chemical compound, we follow these ratios to get the certain amount of products without wasting our reactants. Okay. So we are going to learn that mathematically. So we are going to learn how much grams of a reactant required to produce certain amount of products. Like let's say I want to produce 25 grams of carbon dioxide. So at the end of this class, we are going to learn how many grams of each required to produce that amount of carbon dioxide. Okay. So those are called mass to mass calculation. So this is going to be a long chapter. Okay. So this is the beginning of a long calculation. Okay, so let's do another example. So I'll get another hydrocarbon. So let's use propane. So propane is C3H8. So this is going to be another combustion reaction. So I'm not going to write the physical state. All are gases. My next reactant is oxygen, carbon dioxide, water. Okay, so these are the products. So now, when you see a chemical reaction, first step is to count number of atoms. Okay, so you're not going to do anything else with a chemical reaction. So first step is counting number of atoms. So first we are going to identify the elements. There are 3 different elements present on reactant side and the product side. Those are carbon, hydrogen, and oxygen. Okay, so reactants and products. Next step is the count. How many carbon atoms are on reactants? What is the total number of carbon atoms? Carbon only. It's 3. How many hydrogen? 8. How many oxygen? 2. Oxygen is a diatomic molecule. It has 2 oxygens. The next one. How many carbons on product side? 1. How many hydrogens? 2. How many oxygens? 3. Okay, so that's the first step. Now we can see it is not balanced. All 3 are different. So now we are going to balance this reaction. So this is the next most important. We can't randomly start from any element. You can do that, but sometimes if you did not pick your right element to start, it might be difficult. Okay. So one trick that you can use during the balancing chemical reaction is by looking at the reaction, identify diatomic molecules like this, or single type of elements like, let's say we have a reaction with iron. Okay. So let's say one of the reactants or product is iron. So if it is a single element or diatomic molecule, keep that element for the last. The reason is when you change this number, it will not change carbon or hydrogen. But if you change a number here, here, or here, it will affect on at least two different elements. So we are going to start from those type of elements. So in the best one is carbon or hydrogen. Okay, so we can start from carbon or hydrogen. So normally what I pick, I'm going to pick one of the reactants, element present in one reactant and one product. Okay, so like carbon present in one reactant with another element, and carbon present in one reactant, one product with another element. So those type of elements are the best one to start. So in this case, we can start from carbon or hydrogen. Normally, combustion reaction, we always start from carbon. It's 3 versus 1. So we need 3 carbon atoms on this side. So the only way to get carbon is by adding carbon dioxide molecules. So since we need 3 carbon dioxide, 3 carbon, we're going to change this number into 3. So now we have 3 carbon dioxide molecules, each has 1 carbon atom. So 3 times subscript is 3. And then it will change number of oxygen because carbon dioxide comes with oxygen. So new number of oxygen is going to be 3 times 2. So 6 from carbon dioxide, and there's 1 in water. So 6 plus 1. So make sure you update other atoms. Okay, so if you did not update oxygen, it is very difficult to balance that reaction. So you have to update all your elements when you change the number. The next one is hydrogen, 2 on product side, 8 on reactant side. So we need 8 from this side. Since each water molecule has 2 hydrogen, so we need 4 of those. So we are going to add 4 in front of water. So 4 times 2 is the new number of hydrogen, 8. And also it will add more water molecules. So now oxygen atoms. So new number of oxygen from water is going to be 4. Because each water molecule has 1 oxygen. So there are 4 water molecules. So 4 times 1 is 4. And there are 3 carbon dioxide, each has 2. So 6 plus 4. New number of oxygen is 10. Okay, so now at this point, we have balanced carbon and hydrogen. So last one is oxygen. So oxygen is a diatomic molecule. So we can get the required amount of oxygen on reactant side by changing this number. Okay, so what is the number in front of oxygen? 5. So it's 2. Each has 2. We need 10. Each has 2. So that number divided by 2 will give the required. So now it's going to be 10, and this is 1. This is difficult. Okay, so let's do more examples. Okay, so I'll give you another hydrocarbon. The next one is going to be C5, H10. Again, CO2. Okay. So this is the first one, and it's very straightforward. That's easy, like the previous example. The next one, we can try this. 4 H10 oxygen, carbon dioxide, and water. So I'll give you a few minutes to try those 2 questions. Second one is difficult. Let me see. Let's change this into 12. That's 12. I change the first one, number of hydrogen is 12. How many of you finished the first one? Okay, good. How many of you did the second one? One. Okay. What is the number in front of oxygen when you balance the first one? Eight. Right, that's good. What is the number in front of oxygen when it is balanced? The second one. I'll give you another minute. So let's start from first one. So how many carbons? 5. How many hydrogen? 12. How many oxygen? 2. The product side, how many carbons? How many hydrogen? How many oxygen? 3. Okay, so now we can see all three are different. So we are going to balance carbons. So how do we balance carbon? So what is the number required in front of carbon dioxide? 5. Because we need 5 carbons. We need 5 carbon dioxide. So 5 times 1 is 5. So new number of oxygen. So what is the new number of oxygen in this side? 5 times 2, 10. And 1 from this. 10 plus 1, 11. Okay. So don't forget to update those numbers. So next one, hydrogen. 12 versus 2. What is the number required in front of water? What is the number? 6. Okay, so 6 times 2. So what is the new number of oxygen? So still we have 10 from carbon dioxide. So new number of oxygen from water is 6. 10 plus 6, 16. Now we are going to get 6 oxygen to reactant side. Is each oxygen molecule has 2. We are going to divide that number by 2. 16 divided by 2 is 8. That's the required number of oxygen molecules. Okay, the new number of oxygen is 16. So 5, 12, 16, 5, 12, 16. The reaction is balanced. Does anyone need more time to note down this? Good. Okay, let's move on to the next one. Same thing. Carbon, hydrogen, oxygen. Carbon, hydrogen, oxygen. Did anyone balance this reaction? No? What is the number in front of oxygen? Yeah. No. Okay, we'll see. I don't think it's 10. So carbon, how many carbons? 4. 4. How many hydrogen? 10. How many oxygen? 2. Product side would be same. 2, 3. Okay. So now again we are going to start from carbon. 4 versus 1. So that number is 4. Okay, so we have to update numbers. 4 times 1, 4 carbon. New number of oxygen, 4 times 2, 8. Plus 1. So that's the new number of oxygen. Sorry, 9. Maybe you're right. Okay, so 8 plus 1 is 9. What's that one? Sorry. So 9, my bad. 9 oxygen. So there are 8 oxygen in 4 carbon dioxide plus 1 water molecule. So altogether 9. The next one, number of hydrogen. So it's 10. So we can change that number here. It's going to be 5. Okay. So then this one change into 5. 8 plus 5. 13. That's a new number of oxygen. 13. So we have correct number of hydrogen. 5 times 2 is 10. So we balanced carbon, we balanced hydrogen. Now new number of oxygen. 30. So how do we get 13 oxygen from this? Yes.
Do we put 2 in front of CH?
Yes.
Or H10,
Yes.
and go back through the whole process?
Exactly. Yes. So now we can see this side is going to be always even. 2, 4, 6, 8 like that. Okay. So since we have an odd number on this side, so simply we can make it even by multiplying 2. So when you multiply by 2, you have to multiply all the balanced coefficients. So except oxygen, we balanced all the other coefficients. So we are going to multiply all those stoichiometric coefficients by 2. So simply we are going to add 2 in front of this because initially it was 1. So we are going to use 2. So we balance this. So we change that into 8. So we balanced water. We are going to change that into 10. So simply we multiplied by 2. So when we do that, all these numbers are going to multiply by 2. So 2 times 4, 8. 2 times 10, 20. Okay. So it didn't balance oxygen. So now new number of carbon, 8 times 1, 8 carbon. Okay. So new number of hydrogen, 2 times 10, 20. Okay, so now we can count new number of oxygen. It's going to be 13 times 2, 26. So you can see 8 times 2, 16 from carbon dioxide. Okay, and 10 times 1, 10. So 10 plus 16, which is equal to 13 times 2, 26. Okay. Yes, so now we need 26 on this side. It's going to be 13. 13 times 2 is 26. So when you have a situation like odd and even count on both sides of the reaction, sometimes we have to make it even and even. Sometimes it's going to be odd and odd. Okay, so most of the time it's going to be even and even. When you have a situation like odd and even count.
Okay, I did all of that, but I skipped all of that, and I don't know how I did it.
It's fine. So if you can do that, so I can do all this without doing this stuff. So if you can do that, that's fine. Really good. Okay. So don't afraid to change any of the balanced numbers, but you have to do it systematically. So if you're going to change those numbers, you have to multiply everything by 2 or 3, something like that. So you can multiply it by 2 and 3. If it is not a balanced coefficient, that's fine. Okay, so like this oxygen. So we didn't balance it. If you're going to change any of those numbers, you have to do it systematically. Okay, so these are combustion reactions, but there are some other reactions. So let's learn a couple of those reactions. Okay, so this is another simple reaction. The next example, P4H10 plus water produce H3PO4. Okay, so this is an acid. Dibromide, what is the name? Does anyone remember that acid? Phosphate into phosphoric acid. Okay. So your element quiz is going to not element quiz, my bad. So naming quiz is going to be next Monday. Okay. So now this is a chemical reaction and it is not balanced. So let's count number of atoms. Phosphorus, hydrogen. Okay. And also we have oxygen. So there are 3 different elements on reactant side. Product side, there's one product. It has 3 different elements. Those 3 different elements are phosphorus, hydrogen, and oxygen. Okay. So now we are going to count number of atoms from each element. So how many phosphorus? 4. How many hydrogens? 10. How many oxygen? 1. Okay, so next one, phosphorus. How many? 1. How many hydrogen? 3. How many oxygen? 4. All numbers are different. Yes.
On the reactant side, would it hydrogen be 12?
Oh yeah. Thank you. Let me say. Thank you. The total number of hydrogen in 2 different molecules. It's going to be 10 plus 2, 12. Okay. So now we are going to pick an element. Okay. So when I pick an element, you can start from phosphorus, or you can start from hydrogen. So no, hydrogen is not good. So I'm not going to start from oxygen. So maybe we have to start from phosphorus, because phosphorus is for one on this side. Okay, so definitely we need more phosphorus on product side. So by looking at your reactant and product, so definitely need more phosphorus on product side. So it will change the count on hydrogen and oxygen. So I'll start from phosphorus. So since it's 4 on reactant side, we need 4 on this side. The new number is going to be 4 phosphoric acids, like that. It will change the count on all 3 elements. The new number of hydrogen, 4 times 3, 12. Okay. So 4 times 1 is new phosphorus, is 4. 4 times 4 is 16. Okay, so now we have new count. So now you can balance hydrogen or oxygen, because when you balance hydrogen or oxygen, the other element is going to balance automatically. Okay. So yes. So it's 12. So okay, so something is wrong. So let me see. Probably I will give you the correct formula. Because we'll look at that. So this is on my worksheet. Worksheet 1. Okay, so this is the mistake. So it is P ordered. It will change our count. So it was a wrong reaction, so that's why we can't balance, we can't use these numbers. Let's do it from the beginning. So that's the correct reaction. Okay. So P for ordered is a formula for the first reactant. Okay. So now let's count it again. P4 for phosphorus. So now new number of oxygen is going to be 10 here plus 1. 10 plus 1 is 11. Okay, that was mistake. The next one, number of hydrogen is 2 because it's in order. Product side, that count does not change. 3 hydrogen, 1 phosphorus, oxygen. Okay, so now we have to decide which element to balance. Again, it's still the same. So it's going to be phosphorus, because definitely we will need more phosphorus on this side. So 4 versus 1, it's going to be 4 phosphoric acid. Okay. Yes, so then we will have the count here. 4 times 3 is the new number of hydrogen, 12. So 4 times 1 is the new number of phosphorus, 4. 4 times 4, 16. Okay. So now we can balance hydrogen or oxygen. Okay, so if we're going to balance oxygen, we already have 10 here. We're not going to change this number. So required is 16. Since we have 10 here, we need 6 more oxygen from this. It's going to be simply 6 in front of this. If not, we can start from hydrogen. The required number of hydrogen is 12. So we have only 2. So we need 12 from water. It's going to be 6. So you can balance it from hydrogen or oxygen. And when you do that, the other one is automatically balanced. So 6 times 2 is 12. And 6 times 1 is 6. 6 plus 10 is 16. So that's the new number of oxygen. So now that reaction is balanced. Okay, so 1 in front of this, 4 and 6. Okay, so let's go over my slides. So there are more examples, and those are easy examples. So we finish this slide. Okay, so this is a simple reaction. Now we can see aluminum and sulfur produce aluminum sulfide. So this is the ionic compound. That formula is fixed. So that formula comes from the charges of aluminum and sulfur. First step is to count number of atoms. So since it's pure aluminum and pure sulfur, you can get number of atoms at 1 and 1. So in aluminum sulfide, there are 2 aluminum and 3 sulfide. So now we can see it's an unbalanced reaction. So then we are going to change these numbers to balance. Since these are individual elements, it is easy to balance that reaction. So we need two aluminum atoms, three sulfur atoms to make one aluminum sulfide. So proper ratio is going to be two aluminum to three sulfur atoms. So then it will be same compound. Okay, so this is the imbalance reaction, and let me write that reaction so it doesn't have the reaction. Okay, we have it now. So balance the chemical equation when solid Fe3O4. So you have that formula, solid Fe3O4 reacts with hydrogen gas. So hydrogen gas is a diatomic molecule. It's a molecule like this. That's the second reaction. And then it produces solid iron. Solid iron gives the pure iron and water. So water has this formula. So now I'll give you a minute to balance this reaction. Okay, so let's count number of atoms. How many iron atoms on reactant side? Three. How many oxygens? Four. How many hydrogens? Two. How many ions on product side? One. How many oxygen? One. How many hydrogen? So now we have to decide which one to start. So by looking at this reaction, we are not going to start it from hydrogen or iron. Okay. You can start it from iron and base, but normally I'm going to start it from oxygen because oxygen present in a compound with another element on one reactant and one product. So I will pick something like that. So 4 versus 1. So we need 4 oxygen on product side. So I'm going to add 4 water molecules. So now my hydrogen and oxygen is going to change on product side. New number of hydrogen is 4 times 2, which is 8. New number of oxygen is 4, and we balanced oxygen. Okay, so now we can balance iron or hydrogen, it doesn't matter because both are same type of atoms. So new number of hydrogen is 8. So we need 4 from this, get 8 hydrogens. And now we have 3 ions on reactant side. We need 3 on product side. It's 1, 4, 3, 4. Any question? Okay, so I'll come to that reaction later. You should be able to balance first 2, A and B, not the last one. If you can balance the last one, that's good, but I will teach you that. So it's a different type of reaction. Okay, so what is the answer to A?
Yep.
Okay, so let's try to find the answer. So this is going to be the count: 2 iron, 3 oxygen, 1 carbon. Product side: 1 iron, 2 oxygen, and 1 carbon. Okay. So now we can decide which element to start. Again, I'm not going to start it from iron or carbon. So oxygen is the first one to balance. If we start from oxygen, it's going to be really easy. So if you start from iron, it might be a little bit difficult. Okay. It's fine. So now we can see we have a situation like odd and even. Okay. Product side even, reactant side odd. So the thing that we can do is add more oxygen to make it even. Okay. So now I'm going to change the number in front of iron oxide, iron 3 oxide. So new number of iron is 4, new number of oxygen is 6. So simply I multiplied it by 2. So now I can get 6 oxygen from this side, adding 3. 3 times 2 is 6, and it will change number of carbon. The new number of carbon is 3. So now we can balance iron and carbon because those are individual elements. The new number of carbon is 3 on product side 1 here. So we need 3 carbon and iron 4 versus 1. So we need 4 iron. 2, 3, 4, 3, answer is 2. And those are the stoichiometric coefficients. Next example. Okay, so aluminum 1, iron 1, oxygen 1. Product side 1 iron, 2 aluminum, 3 oxygen. Again, oxygen is the best element to start. 1 versus 3, so it's 3, 1. So we can get 3 iron oxide, iron 2 oxide. It will change number of oxygen into 3 and number of iron into 3. So now we can balance aluminum and iron. So 3 iron, we need 3 on this side. 2 aluminum, we need 2 aluminum on this side. 2, 3, 3, 1. So we will change this number. Answer is 1. Let's do some examples like C, because you should be able to recognize this group. So what is this group? SO4. What is that group? It's a polyatomic ion present in an acid. So that's a sulfuric acid. So we are not going to split those type of groups into individual elements. So that's why it is different from other reactions. So when you see a chemical reaction like this, so as an example, we have a compound in between sodium ion and phosphate ion. Phosphate ion is PO4 minus, sodium is 1. So 3 goes to sodium, 1 goes to phosphate. And that compound is sodium phosphate, Na3 PO4. So we can dissolve this into water because this is the ionic compound and physical state is aqueous. So we can mix this chemical with another chemical, and that chemical comes from magnesium and chlorine. Magnesium is 2 plus, chlorine is -1. So 1 goes to magnesium, 2 goes to chlorine. Correct formula is MgCl2. So that's my second reactant, MgCl2. Aqueous. It's another soluble salt. Okay. So I'm going to erase this. And that's how these formulas comes into the reaction. And this is another type of reaction. And we're going to talk about these type of reactions from chapter 4. And the name given for these reactions are called double displacement. Double displacement type reaction. So magnesium replace sodium and sodium replace magnesium. So that's how we get the products. So magnesium is going to combine with this anion and sodium is going to combine with this anion. So products are going to be magnesium ionic 2 plus, phosphate is PO4 minus. Correct formula is going to be Mg. 3 goes to magnesium, 2 goes to phosphate. Now we have 2 phosphate groups in the formula. So this is our first product, magnesium phosphate. Magnesium phosphate is going to be like that, and it's aqueous. The other product comes from sodium and chlorine, anion and cation. So it's exchange. Sodium is +1, chloride is -1, +1, -1 cancels out. So second compound is NaCl. So also soluble. Now we have imbalanced reaction. And that's going to be our reaction to balance. So we have this on slide 14. Sodium phosphate, magnesium chloride, magnesium phosphate, and sodium chloride. Why this reaction is different? It is different because it has a polyatomic ion. So when there's a reaction with a polyatomic ion, and if it is present on both sides of the reaction, okay, so reactant side and product side, you should be able to identify those polyatomic groups and don't split those polyatomic groups into individual elements. So when you count number of atoms, we are going to keep it as a single unit. Okay. So this comes from sodium and phosphate. So we have sodium ion and phosphate ion. So we are going to keep that polyatomic group as a unit. Okay. So one unit here, and there are 2 units on that side, same group. So next compound comes from magnesium and chloride. Magnesium is 2 plus, chloride is -1. Charges are not required for this one, but you can write charges. That's really good. Okay, so product side, sodium, it is present in sodium chloride. We have sodium ion in sodium chloride. And also we have phosphate ion in magnesium phosphate. So we're going to keep it as a unit. The next one is magnesium. It is present in magnesium phosphate. And last one is chloride in sodium chloride. So we have same ion and same polyatomic ion on both sides of the reaction. This is the important part. Don't split polyatomic ions into individual elements. Because sometimes we will have same polyatomic, 2 different polyatomic ions with the same element like NO3 minus and NH4, 2 minus. If we split these into nitrogen, oxygen, and sulfur, I don't think you're going to balance that reaction forever. Okay, so if you're really good, you will balance, but otherwise it will be very difficult. Okay, so when you see polyatomic groups, keep it as a separate unit. Okay. Now your starting point is going to be your polyatomic group. That's the most complicated one. So, sorry, let's count number of ions. So there are 3 sodium ions and 1 phosphate, 1 magnesium, and 2 chloride or chloride ions. Product side, sodium chloride, 1 sodium, 1 chloride. Magnesium phosphate, 3 magnesium, and number of polyatomic group is going to be the number outside of the parentheses. Okay. So that's the count. So now your starting point is going to be the polyatomic group. 2 versus 1. So we need 1 more phosphate group. So we're going to get another sodium phosphate. So we're going to add 2 in front of this. So 2 times 3, new number of sodium is 6. And there are 2 sodium phosphate. And we will get 2 phosphate. Because each sodium phosphate has 1 phosphate group. There are 2 of those, 2 phosphate groups. So we have balanced phosphate. So now next one, normally I will balance the largest number. So in this case, we have largest number on sodium ion. So next one to balance is the largest count is 6. So we need 6 sodium chloride. 6 sodium ion, and also it will change number of chloride into 6. The next one you can start from any of the 2 remaining ions. So when you balance one, the other one will automatically balance. So you can start from magnesium or chloride. Okay, so if you want to balance magnesium, it's 3 versus 1. So we need 3 from this. 3 times 1 is 3 magnesium. 3 times 2 is 6 chloride. Last one will automatically balance. 6 to 3 is 6. Any question? You will get 1 or 2 like this in the exam and 1 or 2 like the previous one in the exam. Okay, so now you should be able to balance the last one because it has a polyatomic group and it's a simple reaction. So just one aluminum ion and two H plus ions, one sulfate group. So two aluminum ions, three sulfate ions, and two H plus ions, or two hydrogens. Okay. So now we can balance, and we are going to balance sulfate ion first, 3 versus 1. So we need 3 in front of sulfuric. So it will change number of sulfate into 3, and 3 times 2 mean number of hydrogen is 6. So we can balance hydrogen or aluminum. So 2 aluminum versus 1, we need 2. We'll change number into 2. 2 versus 6, so we need 4 more here, so altogether it should be 6, 3. So 2, 3, 1, 3, 2, 3, 1, 3, 1, 3, 2. Okay. Let me give you another reaction like this. That reaction is going to be potassium nitrate and carbonic acid. Potassium nitrate and carbonic acid. Potassium nitrate is KNO3. Aqueous. Carbonic acid is H3O3. Aqueous, double displacement. So potassium is going to combine with carbonate and produce potassium carbonate, K2CO3. Aqueous plus hydrogen combined with nitric and produce nitric acid. Okay, so you should be able to name all these compounds. We have learned that from chapter 2. First one is potassium nitrate, next one is carbonic acid, next one is potassium carbonate, last one is nitric acid. I'll give you a minute to balance this reaction. Now we can see there are 2 polyatomic groups and each has oxygen. So if you split oxygen, it will be difficult. This is an ionic compound between potassium ion and nitrate polyatomic ions. So 1 potassium and 1 nitrate. Don't use 3. Okay. So nitrate is NO3 minus. There's only one of those units. The next one is hydrogen and CO3. So carbonate, H plus, and carbonate. Carbonate is 2 minus. So H plus, there are 2. That's an acid. Carbonate, 1 carbonate group. Product side, potassium ion. There are 2 of those. And next one is nitrate. The nitrate presenting nitric acid. We have only 1. Next one is H plus. So we have only 1 H plus ion in nitric acid, and last one is carbonic ion. CO3 2 minus 1. So 1, 1, 2, 1. So it is unbalanced. Okay. So now we have 2 choices. Nitrate. Nitrate is already balanced. The other one is carbonate. Carbonate is also balanced. Yes. Okay. So if both are balanced, then we can move on to a different one. So it's 2 versus 1. So we need 2 potassium. And when you balance potassium, it will change number of nitrate. So you should be able to update those numbers. It's 2, so it will change number of potassium into 2. That's fine. But we are going to change number of nitrate into 2. Okay, so then you have to balance this again. So 2 nitrate versus 1 nitrate, and we need 2 nitric acid. So when we change that, it will change number of nitrate and number of hydrogen. Number of hydrogen is 2. Okay, so now I think that reaction is balanced. So 2 potassium, 2 nitrate, 1 H plus, 1 H plus, sorry, 2 H plus, 2 H plus, and 1 carbonate. So that's the balanced reaction. 1 here, Any question? Okay, I'll give you another reaction like this. So it has 3 polyatomic ions in one reaction. So this is the next example. So this is going to be ammonium phosphate, NH4 phosphate. So we need 3 from this. Plus one is going to be nitrate and it's lead nitrate, I guess. Yes. Lead 4 nitrate. So lead is a transition metal, so charge is 4 plus. So we are going to neutralize that using 4 nitrates. Lead 4 nitrate. Produce lead with phosphate, produce lead 4 phosphate. So lead 4 phosphate is going to be this one. Plus next one is going to be ammonium and nitrate. Ammonium nitrate is 1 to 1. Formula is this one. Okay. I'll give you 2 minutes to balance that reaction and then I'll explain it. Did anyone balance it? What is the number in front of the last product, ammonium nitrate? 12. Did everyone recognize the 3 polyatomic ions present in that reaction? There are 3 different polyatomic ions, ammonium, and then phosphate and nitrate. So there are 3 different polyatomic ions and lead 4 ion. So this is a single unit, NH4 plus, because we have the same unit in this compound, NH4. Next one, phosphate, PO4, 3 minus, so you can see it here and also here. And last one is nitrate, nitrate on both. Okay, those are the polyatomic groups. And in addition to that, this compound has lead 4. So transition ion, transition metal. Okay. Product side, NH4 plus, phosphate 3 minus here, and nitrate minus that. Okay. So last one is lead. So if you split nitrogen and oxygen, you can see it's present in 2 different polyatomic groups. So it's going to be a mess when you split those into individual atoms. But if we can recognize these groups, it's really easy. Okay. So simply we are going to count number of units and number of ions. So ammonium, how many ammonium ions in the reactant side? How many ammonium ions in the reactant side? 3. So this number is the number of ammonium groups. So how many phosphates? No parenthesis, single unit, 1. Okay. So how many nitrates? 4. So this number is number of nitrate groups. Number of lead? 1. So let's do the same thing for product side. Ammonium 1 and it has nitrate. So nitrate is also 1. Cation and ion. And number of phosphate? 4. And number of lead? 3. Okay, so now we have 3 different polyatomic ions. So normally I start from the largest count. Nitrate, phosphate, same count, but I will start from phosphate because it comes with lead. So I'll start from phosphate. So 4 versus 1. So we need we need 4 phosphate on this side. So it has to be 4 from this compound. So each has 1. So we need 4 of those. 4 times 1 is 4 phosphates. And it will change number of ammonia. So 4 times 3 is the new number of ammonia. 12. So the largest number is on ammonium. We can balance ammonium. Has to be 12. Each has 1. So we need 12 of those. It will change number of ammonium into 12, and also at the same time it will increase number of nitrate into 12. The next one is nitrate. 4 versus 12. So each has 4. We need 3 of those. 3 times 4, 12. Now you can see we have the same count for all polyatomic groups. And if now we can count number of atoms, it will be same. The only thing that we didn't balance is lead. 3 versus 1. Lead will automatically balance. Okay, so 3 lead. And if you're going to split those into nitrogen, oxygen, and phosphorus, I don't think it is easy to balance. Any question? Do you need more example like this, or is it enough? Do you need more example, or is this enough? So if you don't need more examples, I'm planning to do the lecture until 2:55. So do you need a break? We can take a break for 5 minutes and then continue the lecture. So let's take a break and continue the lecture.